What is the nature of the round-off error here? Can someone help me unpack what exactly is going on under the hood here? I'm on 64-bit Python 2.7. For the first, I would assume that since there is only a precision of 15 for float that it's just round-off error. The true floating point answer might be something like. And the decimal just gets lopped off. But the second result makes me question this understanding, and can't one be represented exactly? Any thoughts? Edit. Just to clarify. I'm not in any way suggesting that the answers are wrong. Clearly, they're right, because, well, they are. I'm just trying to understand why.
It's just rounding as close as it can. 1 times 10 to the power of 16 in floating hex is 0x4341C379337E08000. 1E16 plus 2 is 0x4341C379337E08001. At this level of magnitude, the smallest difference in precision that you can represent is 2. Adding 1.0 exactly rounds down, because typically IEEE floating point math will round to an even number. Adding values larger than 1.0 will round up to the next representable value.
Output. Let's decode some floats and see what's actually going on. I'm going to use Common Lisp, which has a handy function for getting at the significand, aka mantissa, an exponent of a floating point number without needing to twiddle any bits. All floats used are IEEE double precision floats. That is, if we consider the value stored in the significand as an integer, it is the maximum power of 2 available. 45035996273704996 equals 2 to the power of 52, scaled down, 2*-52. It isn't stored as 1 with an exponent of 0 because it's simpler for the significand to never have zeros on the left, and this allows us to skip representing the leftmost 1 bit and have more precision. Numbers not in this form are called denormal. Let's look at 1 times 10 to the power of 16. Here we have the representation 50000000000000000 2 to the power of 1. Note that the significand, despite being a nice round decimal number, is not a power of 2. This is because 1 times 10 to the power of 16 is not a power of 2. Every time you multiply by 10, you are multiplying by 2 and 5, multiplying by 2 is just incrementing the exponent, but multiplying by 5 is an actual multiplication, and here we've multiplied by 5 16 times. Observe that this is a 53-bit binary number, as it should be since double floats have a 53-bit significand. But the key to understanding the situation is that the exponent is 1. The exponent being small is an indication that we are getting close to the limits of precision. This means that the float value is 2 to the power of 1 equals 2 times this significand. Note that the issue here isn't even that decimal numbers aren't exact in binary. There's no binary repeating decimals here, and there's plenty of 0 bits on the right end of the significand, it's just that your input neatly falls just beyond the lowest bit.
With number py, you can see the next larger and smaller representable IEEE floating point number. So, and therefore 1 times 10 to the power of 16 plus 1.1 is correctly rounded to the next larger IEEE representable number of 100000000000000000002.0, as is. And 1e16-, something slightly larger than 1, is rounded down by 2 to the next smaller IEEE number. Keep in mind that 32-bit versus 64-bit Python is irrelevant. It is the size of the IEEE format used that matters. Also keep in mind that the larger the magnitude of the number, the epsilon value, the spread between the two next larger and smaller IEEE values basically changes. You can see this in bits as well.
If you want to support the channel, please consider liking and subscribing.